Alright, welcome back to your video classroom grade 11s. In today's lesson, we'll study the sine, cosine, and tangent ratios of special right triangles. This is also in section 2.1, which starts on page 74. It's part 2 of the lessons on 2.1. So we're going to focus, as you see here, on determining the exact values of the sine and cosine and tangent ratios in a 30, 60, 90 triangle or a 45, 45, 90 triangle. And we're going to look at how we can use that information or that skill set to solve some problem with trig ratios. So first, let's learn about these two special triangles. You'll see that they're both triangles with right angles. We call this one the 45, 45, 90 triangle. It's an isosceles triangle with sides of 1. And if we use Pythagoras' theorem, we could calculate that the hypotenuse of that triangle has to be root 2. The other triangle is actually half of an equilateral triangle with sides of 2, 2, and 2. But we don't use this part. We cut it in half, in fact, so that we have a base of 1, a hypotenuse of 2, and again we can use Pythagoras' theorem to calculate that c squared minus a squared equals b squared, and we get root 3 as the height of this triangle. This triangle, this 1, 2, root 3, has angles of 30, 60, and 90 degrees. Now, using information that we have about sine, cosine, and tangent, we've already seen that the sine of an angle is equal to the opposite side over the hypotenuse. So we can use that information here and say that the sine of 45 is equal to its opposite side, which is 1, over the hypotenuse, which is root 2. The cosine of 45 is the same thing. Since it's an isosceles triangle, the adjacent and the opposite are the same. And the tangent of 45, which is opposite over adjacent, is equal to 1 over 1, or simply 1. Now, we do need to be aware of a couple things, and one of that is that we can rationalize the denominator. We can get rid of a radical in the denominator by multiplying the numerator and the denominator by whatever radical is in the denominator. 1 times root 2 gives us root 2. Root 2 times root 2 is root 4, and the square root of 4 is 2. So this value and this value are equal. Okay, they mean the same thing. We just don't have a radical in the denominator. Now, sine of 30, so we look at 30 over here. Its opposite side is 1, and the hypotenuse is 2, so we get 1 over 2. Cosine of 30, the adjacent is root 3, and the hypotenuse is 2, so we get root 3 over 2. No need to rationalize here because the radical is already on top. And the tangent of 30 is opposite over adjacent, so we get 1 over root 3. And if we multiply that top and bottom by root 3, we get root 3 over 3. And finally, the sine of 60, let's change some color here. The sine of 60 is equal to opposite over hypotenuse, so root 3 over 2. The cosine of 60 is adjacent over hypotenuse, so 1 over 2. And the tangent of 60 is opposite over adjacent, so root 3 over 1, or simply root 3. So I'd encourage you to make note of all of these values: sine, cosine, and tangent of 45, sine, cosine, and tangent of 30, and the sine, cosine, and tangent of 60. They will come back, and in some of the calculations that you're doing today, you're going to be using something times sine 60, and it's expected that you're going to use the exact value of whatever sine 60 is, or the exact value of whatever cos 30 is, or the exact value of whatever tangent of 45 is. Okay, so keep those handy. Now we're going to use those values of sine, cosine, and tangent to calculate missing sides. So we're going to determine the value of x on 3 different triangles here. So whenever we're looking for a missing side, especially in a right triangle, we can use trig ratios if we know an angle and one other side. So I look at the angle that I've got. I look at the side relative to that angle, so that's the adjacent, and the hypotenuse. So adjacent and hypotenuse means we're going to use the cosine of 45, and that's going to be equal to the adjacent over the hypotenuse. Now, from special triangles, we know that the cosine of 45 is root 2 over 2, or 1 over root 2, whichever we prefer. So I'm going to write that as 1 over root 2 is equal to 25 over x, because the cosine of 45 is 1 over root 2. To get x by itself, you can multiply both sides by x, and to get rid of the root 2 in the denominator, I'll multiply both sides by root 2. And that's going to give me x times 1 and 25 root 2. And there you have it. That's the value of x in exact form. Okay, no need to plug it into the calculator, no need to get a decimal. In this next one, given the angle 60, I've got the opposite side and the hypotenuse. So that requires us to use the sine of 60, which is equal to the opposite over the hypotenuse. Sine of 60, we saw previously, is equal to root 3 over 2. So root 3 over 2 is equal to x over 30. And x is in the denominator or numerator here. All I have to do is multiply both sides by 30, and I get x is equal to root 3, or 30 times root 3. I usually write the coefficient in front, the radical second, divided by 2. And 30 divided by 2 is 15, so we get x is equal to 15 root 3. In part C of this example, again looking for the missing side, relative to this 30-degree angle, that's the opposite, and this is the adjacent, so we're looking at the tangent of 30, which is going to be equal to x over the opposite side over the adjacent, or 14. Now, if I scroll back up, we'll see that the tangent of 30 is either equal to 1 over root 3, or root 3 over 3, same thing. Let's just use root 3 over 3 for this one. That's going to be equal to x over 14. And if I want to get x by itself, I just multiply both sides by 14, and x is equal to 14 root 3 over 3. 14 doesn't divide by 3. There is no further simplification that I can do, so I'm left with my answer here in exact form. Now, we mentioned at the beginning that we'd be focusing also on solving problems using trig ratios. So here's an example of a problem. The pendulum of a metronome. A metronome's that machine that you use at piano that goes tick, 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 helps you keep a beat. So the pendulum is 8 centimeters long and moves from a start position of 45 degrees to the other side of 135 degrees. What horizontal distance does the tip of the arm move in one beat? And give an exact answer. So if the metronome starts in a standard position of 45 degrees and then moves over to the other side to 135 degrees, the question is essentially, what's the horizontal distance between the tip of the pendulum from the right side to the other side when it stops at 135 degrees? So we're going to look for this distance x on the one triangle, which is the same as that distance x on the other triangle. So we're going to try to calculate x and double it to get that horizontal distance. Now, in this triangle, I know that the pendulum is 8 centimeters long, so that's the hypotenuse. And if this is 45, we know that this must be 45 as well, because 45 plus 45 makes 90. Also, since this line is parallel to that line, these are alternate interior angles, so this has to be 45. So this is one of those special triangles where the two short sides, x and x, have to be the same. Using Pythagoras' theorem, we can say that x squared plus x squared is equal to 8 squared. That means 2x squared is equal to 64. X squared, if we divide both sides by 2, is equal to 32. And x is equal to the square root of 32. I'll come back to this a little bit later, but the square root of 32 is equal to root 16 times root 2, or 4 root 2. And we'll come back to that little piece of information later. Now, if x is 4 root 2, 2 x's must be equal to 8 root 2. So 2x equals 8 root 2. That means the horizontal distance that the tip travels is 8.2 centimeters. So take note here that anytime I have a problem, especially the word problems, I want to end with a complete sentence. So there's a few things I do. I make sure that I sketch the situation out. I work the calculations out, and then I answer the question. Okay? So usually 3 or 4 points for a question like that. Now here's example 3. I'd encourage you to pause the question or pause the video and read that question out. And once you have it read, I'd also encourage you to sketch the information out onto the diagram, like you see here. Now, we've got these two wires. They're attached at a height of y for the red wire here. That goes from here down to there. And the other wire we'll call a height of x. If we want to find the distance between one wire compared to the other, we need to essentially go y minus x. So that how much higher is the end? Let's say that height is equal to y minus x. So we're going to find y and find x, and then we're going to calculate what h is. So starting with y, we've got the angle of 60, we've got the hypotenuse, and we're looking for the opposite side, which means we're going to calculate the sine of 60 is equal to the opposite over the hypotenuse. That means y is equal to 20 times the sine of 60. And from what we saw before, the sine of 60 is root 3 over 2. So y is equal to 20 times root 3 over 2. 20 divided by 2 is 10. So y is equal to 10 root 3. We do a similar calculation for x over here, which is also the opposite of 30. So again, we're going to do the sine. So the sine of 30 degrees is equal to x over 20. That means that x is equal to 20 sine 30. Sine of 30 is equal to 1 over 2. So that's 20 times 1 over 2. And 20 times a half, or 20 divided by 2, is 10. So we know that x is equal to 10. Since we're looking for the height difference between the two wires, and that's equal to y minus x, we can say that h is equal to 10 root 3 minus 10. And unless we do a calculation with our calculator to get a decimal, which actually is 7.32 meters, usually the question is going to require that we leave our answer in exact form. So exact form will be 10 root 3 minus 10 meters, or if we factor out the 10, it'd be 10 times root 3 minus 1 meters. Either one of those is fine. And then, of course, end with a sentence. So the difference in height between the two wires is 10 root 3 minus 10 meters.